non-parametric estimation technique. In parametric estimation technique, we have talked about linear discriminant analysis. In non-parametric estimation technique, we have discussed about kernel density estimation. Okay, and we took this example where we have a set of data points and set of data points of distribution. So from this distribution, we have drawn 150 points randomly. And on the left hand side here, you can see that these 9 points which define the class densities of each three classes, orange, blue, purple. So for this 9 points, so we will get three peaks in each class. So since we are considering three different classes, orange, blue, and purple, so and these points represent the centroid. Okay, centroid in each class. So since there are 3 points in each class, so that means there will be three peaks in density estimation. So around these points, we get the concentration of the points, and these 9 points represent the class densities of each of the three classes. So when we saw base classifier, so base classifier make the density estimation for orange data, for blue data, and for purple data. And the corresponding predictions we get like on the right hand side here, the regions of points are classified by base classifiers as orange, blue, purple. Okay, and these class boundaries are highlighted in white. So here you can see that these are the class boundaries. So class boundary between purple and blue. Okay, and purple and orange, then orange and blue. So this white color represent the boundaries in between the class densities. Now, when we saw the quadratic discriminant analysis, so we have estimated the class densities as well as the classification decisions are made by quadratic discriminant analysis, and we have estimated the class boundaries as piecewise quadratic. So we have already talked about this piecewise quadratic estimation. So here the estimated class boundaries are found to be piecewise quadratic. And when we talked about linear discriminant analysis, we have estimated the class densities as well as we have made the classifications by linear discriminant analysis, and the estimated class boundaries are found to be piecewise linear. So now we will start talking about maximum likelihood parameter estimation technique. So here the maximum likelihood parameter estimation technique is a procedure of finding the value of one or more parameters for a given statistics. Okay, and this maximum likelihood make the known likelihood distribution a maximum. So first of all, we need to determine one or more parameters for a given statistics, and we will make this zero, because when we get the likelihood function, on when we compute the likelihood function, so we will make that likelihood function become zero to get the maximum likelihood. So two different way we can make this. So we can obtain the likelihood function for the maximum likelihood estimation, and then we take the derivative and make it zero to get the maximum likelihood. Or we can get the log likelihood of this estimation, and then we get the or we take the derivative and make it zero to get the maximum log likelihood. So maximum likelihood is a relatively simple method for constructing an estimator for an unknown parameter theta. Now, if we consider the parameter to be determined is theta, then the maximum likelihood maximum likelihood estimator for the parameter theta becomes theta cap. So we can represent the maximum likelihood with this notation theta cap. So here the maximum likelihood estimation can be applied in most problem and often yield a reasonable estimator of theta. So here what we do, we consider the random variables x1 to xn. Okay, random variables x1 to xn which form a random sample from a distribution f of x given theta. And here capital X is the continuous random. If the capital X is found to be continuous random variable, then f of x given theta is a probability distribution function. Or if capital X, this random variable is found to be discrete random variable, then f of x given theta is a point mass function. Okay. So here we use the given symbol to represent that the distribution also depends on parameter theta, where theta is a real valued unknown parameter or a vector of parameters. So here theta could be a real valued unknown parameter or a vector of parameters. Now for every observed random variable x1 to xn, so we can define f of x1 to xn given theta is given by f of x1 given theta, comma f of x2 given theta until we get f of xn given theta. Okay. So for every observed random sample x1 to xn, so we can define this function, and this function will give us the likelihood function, and from there we will get the maximum likelihood. Now here we will consider M class problem with feature vectors distributed according to probability of this x given wi. This probability of x given wi is nothing but the likelihood. So this probability represents the likelihood for I equals to 1 to m. And here we assume that these likelihood functions are given in a parametric form. Okay, that means the parametric form is already specified, and that the corresponding parameters form the vectors theta I which are unknown. So here the corresponding parameters that we would like to determine is nothing but the vectors theta I. Okay, so this theta is found to be unknown here. Now to show the dependence on theta I, we can write this likelihood function probability of x given wi parameterized by theta I. Since here the vector theta I is unknown, that we have to determine, and we also need to show this likelihood function is dependent on this unknown parameter theta I. So therefore we can write probability of x given wi parameterized by theta I. Now our goal is to estimate the unknown parameters using a set of known feature vectors. So these feature vectors are known. So we can get the feature vectors from 1 to m number of. So here m denotes the number of classes for which we consider the m number of feature vector. So here the feature vectors are known. Okay, feature vectors are known, and from these known feature vectors we have to estimate the unknown parameters theta. So if we further assume that data from one class do not affect the parameter of other class, so we can say that from x1 to xn with the random samples which are drawn from the probability density function p of x parameterized by theta, and here we form the joint probability distribution distribution function p of capital X parameterized by theta. So here x may contain n number of points x1 to xn. Okay, so here x is found to be a vector. So here x is a set of samples. So here we can assume that these samples are statistically independent, okay, between the different samples. So we can write probability of capital X parameterized by theta given by probability of P of x1 comma x2 comma xn, which is parameterized by theta, and which is nothing but the product over probability of xk parameterized by theta, and k varies from 1 to n. That means since we are having n number of samples uh, for uh, for the random sample x, so we can write this probability function p of theta parameterized by p of x parameterized by theta, which is nothing but the product over p of xk parameterized by theta, where k varies from 1 to n. Okay, that means for each sample we will get this probability, and this will be multiplied with the next the probability obtained from the next sample. So in this way we will get, so if we write this expression in different way, so we can write probability of x1 parameterized by theta comma probability of x2 parameterized by theta. So in this way we can write the probabilities for the set of n number of samples. Okay, and then we get the uh, then we get this product over these probabilities, and when we take the multiplication between these probabilities, we will get this on the probability of this p of x parameterized by theta. This this is a function of theta, since here we parameterize the probability by theta, and this function is also known as the likelihood function. So this function that we are talking about is called the likelihood function of theta with respect to x. So here x is given, theta is unknown. So here x is known, theta is unknown. Since since we are assuming that these samples are statistically independent between different samples, then we could get this likelihood function of theta with respect to x. So here the maximum likelihood method will estimate theta so that the likelihood function takes it maximum value. Now how we will get the maximum value? Because we have to estimate the maximum likelihood. First we get the likelihood function by this expression, okay, and then we get the maximum likelihood. How to get the maximum likelihood? So we will get the maximum of this likelihood function for n number of samples. So this can be represented by this theta cap ml. So we now call this maximum likelihood of theta as theta cap ml. Okay, so this theta cap ml represent the maximum likelihood method likelihood of estimated theta. So here we can write theta cap ml is given by argmax. So product over this probability of xk parameterized by theta for k equals to 1 to n. Okay, so this is the representation for maximum likelihood function, so that we estimate over theta. Now how to get the maximum likelihood for the given likelihood function of theta with respect to x. So for that we need to get the gradient. Okay, we need to get the gradient, and that gradient function, we will make this gradient function 0. That means we have to take the derivative over this product over probability of xk parameterized by theta. So therefore we are writing del of this product over this function with respect to theta. Okay, So here theta, here the function that the probability of x parameterized by theta is found to be objective function. So this function is nothing but the likelihood function. So we have to get the maximum likelihood, which for that we will make it 0. Okay, and to get the maximum likelihood, we will take the derivative, and this derivative will give us the gradient of the likelihood function with respect to theta. Okay, so we are making this function 0 after taking the derivative with respect to theta. So so this is one form, this is one form, and another form is that we can take the log likelihood of this likelihood function. Okay, so the first we get the likelihood function from this expression. So we get the likelihood function from this expression, and then we will take the log likelihood. So log likelihood means here this, if the log likelihood function is represented by this L theta, so L theta will be given by ln product over p of xk parameterized by theta, where k varies from 1 to n. So this will give us the log likelihood function. Now since we need to get the maximum log likelihood, just like maximum likelihood function, so therefore what we will do, we will just simply take the derivative, and this derivative will give us the gradient of the log likelihood function. So this here L represent the log likelihood function. We take the derivative with respect to theta, and this will give us the gradient. We will make this 0. So here we are making 0. Okay, and get a point for the theta where we will get the maximum log likelihood. So similar to maximum likelihood, here we are getting getting a point of theta where we will get the maximum likelihood. So similar to this form, we will get the maximum log likelihood at some point theta. Okay, so this form, so here 2.49 and 2.51, so these two are equivalent to each other. Okay, equivalent to each other. Now here you can see that the maximum likelihood estimator function is drawn over here. So here x-axis the theta represent along x-axis, and here the log likelihood function is represent along y-axis. Now if we consider a point, so this point is determined theta ml. Okay, so at this point we get the maximum, so maximum likelihood function. So maximum likelihood is estimated at point theta ml. Okay, so by gradient we will get this maximum peak at this point. Okay, so at this point we can say that the likelihood function is maximized. Okay, now this function this so this function maximum likelihood estimator illustrate the method for single unknown parameter case. Okay, now we could have a set of such parameters. So the here the maximum likelihood estimate correspond to the peak of log likelihood function. So as I said that at this point we get the maximum peak, and this peak represent the maximum log likelihood or maximum likelihood for this maximum likelihood estimator. So the maximum likelihood estimation has some very desirable properties. If theta 0 is the true value of the unknown parameter in p of x parameterized by theta, then it can be shown that under generally valid conditions the following are true. So we can have some properties of maximum likelihood function. Now why the theta is called the true value? If theta 0 is the true value of the unknown parameter in this function, in this likelihood function, then it can be shown that under such valid conditions the following are to be true. Okay. Now the true value means if I say that truth value of 1 plus 1 equals to 3 is false, so that means the truth value for theta 0 is found to be true. Okay. If in other way we can say that as the truth value of 7 is odd, that means this statement is found to be true. So similar to this statement, we will get a truth value for theta 0 is found to be true. Okay. So this true value of the unknown parameter in this function, so we can see that under some valid conditions, the following properties are found to be true. So the first property we will be talking about that the ML estimate is asymptotically unbiased. What do you mean by asymptotically unbiased? That means the biased function converges to zero, which is in other way known as this asymptotically unbiased. So the maximum likelihood estimate is asymptotically unbiased. So which by definition means that so we, so here we are taking the limit. So limit of this estimation over theta cap ml equals to theta 0. So at point theta 0 we get the true value. Okay, and this true value can be achieved by taking the limit n tends to infinity over this estimation. Okay, over this estimation at theta cap ml. Okay. So this will give us the true value at theta 0. So theta 0 itself is a true value for this estimation. So which we can get by taking the limit n tends to infinity over this estimation. And this will give us a true value theta 0. Okay. Now the second property says that the maximum likelihood estimate is asymptotically consistent. Okay, that is, it satisfies if we take the limit, if we take the limit of probability theta cap ml minus theta 0. Okay, so the estimated value and the true value. So we get the deviation between estimated value and the true value. So which is found to be less than equals to epsilon. Okay. So we get some probability over these deviations, and these deviations will be found to be less than equals to epsilon, and this epsilon is arbitrarily small. Okay. So if this limit give us 1, then we can say that the estimate converges in probability. Okay, estimate convergence in probability for large n, it is highly probable that the resulting estimate will be arbitrarily close to the true value. Okay, so that means this, so we can get some interpretation for this asymptotically consistent property, where for a for large n, or if we have the large number of samples, for that it is highly probable that the resulting estimate will be arbitrarily close to the true value. So this is the interpretation of this asymptotically consistent property. So where we take the limit n tends to infinity over this probability of deviations, and these deviations satisfies uh, this deviations is found to be less than equals to some small value. Okay. Now the we can make a stronger condition for consistency, which is found to be also true. So which is given by, so here we are taking the square of these deviations, and then we get the estimate over which we take the limit n tends to infinity, and this will give us 0. So what will be the interpretation for this limit that we are taking over the estimation of square of these deviations? So here we can say that the estimate convergence in the mean square. Okay. So in other words, for if we have the large number of samples, then the variance of the maximum likelihood estimate will tend to 0. Okay. So we can have two more properties. So you can get these properties. You can also go for the proof of these properties, so which can be found in the books that I have sent to you today. Okay. So these first two properties are very important. One is the asymptotically unbiased and the asymptotically consistent. So these two properties are very important. So we can have other two properties like maximum likelihood estimate is asymptotically efficient. Then the probability density function of the maximum likelihood estimate as n tends to infinity, which approaches to the Gaussian distribution with mean theta 0. Okay. So at this point in the uh, uh, at this point, when we take the limit n tends to infinity over the estimation of this square of deviation, so we get 0. Okay. Now we will talk about Gaussian mixture model. Now, what is the general assumption about the density estimation? So if we consider k components, okay, let us consider let us consider k components, and for a particular component so we get this is this w this omega I represent the class to this particular components. Okay, so if we are considering k components, then for ith component we can have the class information as omega I. Okay, now the component omega I, or just omega I, has an associated mean value mu I. Okay, we are having k components. For each components, if ith component is represented by wi, then this wi can have a mean vector mu I. Now here each component generates a data from a Gaussian with mean mu I and covariance matrix sigma I. Okay. Now for each class we can generate the data, or we can generate the density from a Gaussian with mean mu I and covariance matrix sigma. Now we assume that each data point is generated according to the following constraint. Okay. Now we can pick a component at random. So here we can see that in the diagram that here we are having three different mean mu1, mu2, and mu3, and around this mean or around this centroid we can define the density of these three corresponding components. Okay. So as we are talking about k components, now we are talking about three components. Okay, and for these three components we are having mean and covariance matrix. Now around this three means or three centroids, we will define the density. Now what we do, we pick a randomly, we can pick a component. Okay, and then we choose the component I with probability p of omega I, and then the data point will be given by this n of mu I comma sigma I. So this represents the normal distribution. So equation. So when we will fit this in the Gaussian equation or normal distribution equation, then we can get the data or the density with mean and corresponding covariance matrix for a particular component. Now, if the data distributed for like the first examples, then it is very easy to estimate the density, because here we can observe the centroid points or means are clearly, because these three distributions are completely separated from each other. Okay, but if we get the distributions like the second examples, then it is sometimes impossible to uh, uh, estimate the density for the corresponding classes. Now, if we get the distribution like the third examples, then sometimes it may be found difficult, but we can estimate the density by randomly choosing a component or one or more component, and then get the centroid for these components and the corresponding density estimation for those components. Now, if we consider such unsupervised case, then we can have this x1 to xn are known. Then the corresponding probability p of w1 to p of probability of wk are known. This sigma means this covariance matrix, this variance are known. So we can get the probability that an observation from class wi, okay. So if we consider a ith class wi, so the ith component, so the corresponding class wi will give us this will give us the probability. So this probability is nothing but this is called the likelihood, okay. So you can remember this gives us the likelihood estimation. So probability of x given omega I comma mu I to mu k. So this mu I to mu k, so this will the given means, okay, class means. So here we have the class means from mu1 to mu x. So here the probability that an observation from class wi would have value x, and given class means are mu1 to mu x. So similar considerations we can have, and then we define this probability of x given mu1. So for a particular if we consider a particular mean, okay, then probability of x given mu1 comma probability of x given mu2. So we can define this function. Also, we can also define this function by taking the n samples together. So here we get the probability of x1 to xn given mu1 to mu k, okay, for k number of components. So two different way we can define this function. Two different way we can define these functions when the feature vectors are known, when this marginal probability uh, for class information is known, and this variance is known. So when these three informations are known, then we can define such functions in different way. Okay. Now let us consider that for each class, now we will consider a particular class C, and the likelihood function probability of x given y. So this y represent the class information. Now we are considering a particular class C. For that a particular class C, we will get the likelihood function probability of x given y equals to C. Okay. Now how the mixture function how the mixture of Gaussian densities we can determine. Now if there are JC number of mixture component, if we have JC number of components for a particular class C, then how this Gaussian mixture model equation can be written. So we can write probability of x given y equals to C. This is given by summation over WJC, which is multiplied by phi of x given mu JC comma sigma JC. So what we get? So this part represent the normal distribution, okay. That means we get the probability function, in terms of mean and covariance matrix sigma. and this is multiplied with the non-negative weights WJC. Okay, so this function phi of x given mu comma sigma denotes the Gaussian density function. So this part of this expression represent the Gaussian density function in terms of mean and covariance, in terms of mean mu and covariance matrix sigma, and WJC represent the non-negative weights. Okay, and if we take the summation of all the non-negative weights, then this will give us 1. Okay, now we are considering this non-negative weights as well as a JC number of mixture component for a particular class C. Okay, so here the Gaussian mixtures are so this equation give us the Gaussian mixture models. Now how we can fit these Gaussian mixture models? If we consider this Gaussian mixture model for a particular class C, and then we can use two different mechanisms. One is called the expectation maximization. So expectation algorithm we can apply, as well as we will apply maximization in order to get the Gaussian mixture feed to the data points. Okay, so first of all we need to get this function, then we feed the Gaussian mixtures by expectation and maximization algorithms. Okay, so these two are the together these two are called expectation maximization algorithm, and we will talk about this expectation maximization algorithm after a few classes, so that we can take the relevant topics for discussion when we will be going through those topics. So we will be discussing this algorithm also. Okay, so here the number of we also talk about the number of mixture components JC, which can be determined for each class using a model selection criterion. So this model selection criterion we will be talking about in different chapter when we will be talking some other topics, relevant topics. Okay. Okay. Now, if you see this Gaussian mixture density estimate and the corresponding Gaussian mixture predictions for different for different values, that means the here we can consider we can if we consider the number of components different, then we get this two different Gaussian mixture density estimate. Okay, and the corresponding Gaussian mixture predictions are shown on the right hand side. Okay, now we will be talking about a non-parametric density estimation method, which is called histograms. So what is histogram? So histogram is a step function approximation of a density function. So if we consider kernel density estimation, then the histograms have a bandwidth parameter which which is chosen carefully. That means if we get the kernel density estimation, then these histograms will give us histograms will have a bandwidth parameter, and this bandwidth parameter need to be chosen carefully. Now for a particular class C, a bandwidth dependent tiling of feature space X into rectangular cells is given. So if we consider rectangular, we will see that how the rectangular cells are considered for these histograms with for a particular class C and a bandwidth and a specified bandwidth. So this X is given in m dimensional feature space. Okay, so this X is given in m dimensional feature space. So that's why we are writing X equals to r to the power Rm. Okay, so we are considering m dimensional feature space. So the cells, if we consider that rectangular cells, for a particular class C, then the cells will be given by this expression. So RC I1 to IM, okay, I1 to IM, which is given by X1 to XM, that belongs to this feature space, M dimensional feature space, such that I1 multiplied by AC1 less than equals to X1 less than I1 plus I1 multiplied by AC1. Now what is this? Now here the HCJ is the bandwidth parameter. Okay, HCJ is the bandwidth parameter. Now here we are considering a rectangular cells for a histograms for a particular class, where we can get the bandwidth parameter to be multiplied with this, we can say the m number of samples, okay, or we can say the step function approximation. So this I1 to IM belongs to ZM, okay, and here HCJ is a bandwidth parameter for jth feature. So if we consider a particular feature, jth feature, then jth feature, then HCJ means C, here C represent a particular class C and J represent a particular feature in Cth class. Okay, and the corresponding parameter will be called bandwidth parameter. So given any feature vector X and any class C, we can write RC X, and this RC of I1 to IM denote the rectangle, okay, and this rectangle will contain the feature vector X. So feature vector X, this is called this is the index vector, this will represent the index vector I1 to IM, which can be found by IJ given by, so this is the, so we are taking the floor function over xj divided by xc comma j, okay, and this will give us this index vector ij for jth feature. Now for j equals to 1 to m, and since we are considering m number of features, where this notation represent the integer floor of real number. So this ratio will give us a real number, and we are taking the floor function over this real number, and that will represent the integer floor of the estimated real number. Now for any feature vector X and any class C, so let us consider this NC to the power RCX will denote the number of training data of class C. So this will fall in the rectangle RC. RC of feature vector X. RC of feature vector X. Okay. So if this number NC to the NC RCX denotes the number of training data for a particular class C, then this training data, the entire training data will fall in the defined rectangle RC of feature vector X. Now the how to estimate the histogram density. So the histogram density is given by this estimated function. What is the estimated function? Estimated function is this p cap of x given y equals to c. So this estimated function is given by the total number of training. Total number of training data for a particular class C divided by this NC. Divided by NC. Okay. So here we are getting the total number of. So this NC represent the total number of training data for a particular class, and this represent a particular instance. This NC RC of feature vector X, this represent a particular instance which is multiplied by 1 by V of RC, and this V of RC is nothing but the feature vector of bandwidth parameter. Okay, so this capital VRC is given by this vector of bandwidth parameters. So this represents the volume of rectangle cells for class C. Now the whole thing is represented by this by this rectangle grid. Here you can see that. So here we get the partition of x equals to R2. So here we are considering two-dimensional feature space instead of m-dimensional feature space, and this we partition this feature space into a grid of HC1, HC, 1 by HC, 2 rectangles. Okay, and here RC I, J represent the rectangle. So here we can get for each rectangle. So here you can do, first we get the distribution of data points. Okay, and then we get this rectangle. Then we get this partition of grids, and then we get this number of rectangles on this grid, and for each rectangle we will get this estimation. Okay, we will get this estimation. If you have any questions, you can ask me. Otherwise, we will stop now. And we will continue this discussion tomorrow. Okay, that's all for today.
Okay, sir. Thank you, sir.